Catharina. And so it's my pleasure to introduce Catharina Stroppel for her third lecture on representation theory and categorification.
Okay, thanks very much. So I will start again from a different angle. And next time I will bring things together and actually say something about categorification, but not yet today. So I want to start with a motivating example, which was already mentioned by Monica. An example of a duality. So the whole talk will be about different kinds of dualities which show up in representation theory. So I start with the Lie algebra GLN, which is GLNC, so n times n matrices over C. So this is n times n matrices over C. And I can act with GLN, obviously, on C to the n, just in the obvious way, by multiplying a matrix with a vector. So, and then we saw in the exercises that I can then also act on, so let me call this maybe V. I can also act on the tensor product of V via the following rule. If I have a matrix A and I want to act on a tensor product like this, so these xi's are elements in V, I just act on the first vector and keep the other ones unchanged. Plus I act on the second vector and leave the others, etc. up to the last one. So I have this action, and on the other hand, I have a symmetric group action on this. SD acts. So how does SD act? I can take the tensor factors and can just permute them by permuting the tensor factors. And so if you look at this action of GLN, you see I act somehow on each factor in a somehow the same way. So that means when I permute first and then act, or when I first act and then permute, it's the same thing. So these two actions permute. And so there's the theorem, which Monica mentioned already, called the Skew How duality. Which says the GLN action and the symmetric group actions commute. But even more, the operators on each side span the commutator for the other side. So that means, in other words, if you ask which endomorphisms, for instance, would commute with the GLN action, you get exactly all the endomorphisms which come from the SD action and vice versa. The guys which commute with the SD actions are exactly the ones coming from the GLN action. Okay, so I can look at the GL2 example. So here I drew the GL2 example. So we have our two-dimensional vector space with, say, basis E1 and E2. And then I drew here the basis of my GL2, and I have one generator of my symmetric group S2. And then if you choose a nice basis of this V tensor 2, so I chose these four basis elements, and I can draw exactly what the action is. And you see there are three vectors where the symmetric group acts just trivially by the identity, and there's one vector where the symmetric group acts by -1. And then the GL2 does something more complicated, but it only goes between vectors which have the same action for the symmetric group. And if I don't draw anything, then the GL would act by 0. And so that means what you can check here very easily is that the GL2 action commutes with the symmetric group action S2. And this duality helps us to understand the representation theory of the general linear Lie algebra, GLN, in terms of symmetric group and vice versa. So I just want to give you a list of generalizations of this Skew How duality. There's tons of generalizations, and I just want to list a few of them. So for instance, so we saw already now in Monica's talk, but also in the exercises, the Hecke algebra, which is somehow a quantized version of the group algebra of the symmetric group. And so what you can do, you can sneak in a little Q and quantize this vector space, which we had before. And you can act with the Hecke algebra on it. On the other side, you can sneak in a little Q in a GLN version, so you get a quantized universal enveloping algebra. And again, there's a sure-while duality that these two actions commute and they generate each other's commutator. So this is an old result, which I think goes back probably to Jones and has somehow a version which works even in arbitrary characteristic and over arbitrary rings. And as a special case of this, so we saw in the exercises that the temporally Lieb algebra is a quotient of the Hecke algebra if you put for delta this special parameter Q plus Q inverse. And so I make this Hecke algebra smaller, and then on the other side, I can act with the corresponding quantum group still, for GL2 in this case. So in the middle, I have a two-dimensional vector space tensor to the D. So this result is a very old result. So it was first proved for Q equals to 1 by Weil and Rummer and Teller. And then later, I think it was Jones who did it. And then Paul Martin also considered the case, which we saw earlier, the case where this temporally Lieb might not even be semi-simple. But then you can also do things like going to supergroups. So we have a super vector space of dimension, even dimension m or dimension 2n. And you can act with this also symplectic group on it, which is a mix between the orthogonal group and the symplectic group. And then on the other side, the symmetric group gets replaced by this Brauer algebra, which we saw just also now in Monica's talk. And so the parameter is depending on this dimension of this superspace. And again, you have to have commuting actions and they generate each other's centralizer. So this is a pretty, yeah.
Sorry, there is a question in the chat if it's in general Q to the n minus Q to the minus n over this Q minus Q inverse. I guess that it's for the previous.
So in this case, it's Q plus Q inverse. The question is whether there's a minus?
I think that if in general, the delta should be this Q to the n minus Q to the minus n over Q minus Q inverse. Or Karina, if you want to clarify the question, that's.
So it's only for GL2. So this 2 corresponds on the other side to quantum 2. And if you go away from GL2, it's not a temporal Lieb X, and it's something more complicated, quotient of the Hecke algebra, which is not a very nice quotient. One can write it down explicitly, but it doesn't. I don't think this algebra has a specific name, for instance.
Thank you.
Okay. So then you can also do the supergroup GLMN. So these are invertible endomorphisms of a superspace. So this is generalizing the group GLN. And then you still have on the other side the symmetric group. So this is more or less the same thing. So this is a result maybe from the 80s. And then what becomes more interesting is when you take, instead of the vector space V, you take these mixed things. You take tensor V up to some R or something, and then V dual, so here's this little dual, to some power. Then what acts here is what we saw earlier, this vault power algebra. So this was this power diagrams with orientations on it. And then on the other side, the commuting action is the super Lie algebra GLM. And this is again a situation where the algebras are usually not semi-simple. So this is much harder in the symmetry. And then you can ask the question, can we also change the group to some other Y group? So when you want to have another Y group here, say of type B, C, D, then at least for B and C, you can act on the other side with GLN times GLN. So this somehow, this Y group of type B is some colored permutations and in two colors. And this corresponds to these two factors of GLN. And you have again commuting actions which centralize each other. And there's a slight different version for type D as well, which I don't want to mention because it's a bit technical. So this has a long history, this duality, with many contributions from many sides. And then you can also quantize this. So you get a Hecke algebra of type BCD. And then on the other side comes something much more complicated. So this is a so-called quantum symmetric pair. So this is a fixed point Lie algebra of a quantum group with respect to an involution. And then you can go on forever. You can go use something like affine Hecke algebras, as Monica mentioned, affine Temperley-Lieb, etc. So I don't know. You have to stop at some point because I think you can do it for years. So here are just a few examples. Okay. So, but there's one thing which I'm not so happy about when I look at these Schur-Weyl dualities or things like these. There's on the one hand side, in our case of the Schur-Weyl duality, there was the symmetric group. Here it's the Y group or something. And on the other side, it's something very different. It's a Lie algebra or quantum group. So Schur-Weyl duality is quite asymmetric. And you would, I mean, somehow you might expect in the two sides, you might expect if you have a duality that the two sides somehow should play the same role. And I want to generalize now this Schur-Weyl duality in a way so that I get something where the two sides really look much more similar. And I want to start with a combinatorial game. So this is just a game which we play, and at the end you hopefully see why it's something interesting. So I want to consider GLN with the natural representation C to the n, which I call V. V. And this has a basis V1 up to Vn. And so this is one player of this game. It's the player with the color red. And then there's another player of the game. It's GLD. So this is like the symmetric group SD. Again, with the natural representation, now I call it W, which is C to the D, and I take a basis denoted by omega or W1 up to WD. So that's the second player, it's the color green. So these are the two players. And then I can look at the following thing. I can take V tensor W. But I use this funny tensor product rule or tensor product thing which Monica introduced. So this means as a vector space, it's just a tensor product of vector spaces. But I act on it with GLN on the first vector and with GLD on the second vector. So somehow this is red, and this is green, and this is green. And you only see somehow the same color. And so I can do the same thing as before for the single GLN. I can take the wedge product now instead of the tensor product, and I can act on this still with GLN times GLD. Okay, now I would like to understand what this thing is. So let's first go back to the tensor product. What is the basis of this tensor product? A basis is given by a basis for the red thing and a basis for the green thing. So let me say it's Xij, which is Vi tensor Wj, where I runs between 1 and n, and j runs between 1 and d. So this is a basis. Okay, and now the lemma is, it's just a little lemma which says what is the basis of this wedge product. So a basis of this wedge product is in bijection to n dots in a certain grid, in a grid of size, well, let me just write, in an n times d grid, in an n times d grid, with at most one dot per box. So what do I mean by this? Okay, so this bijection is somehow, I want to call it the matrix reading, and you will hopefully see in a second why I call it like this. So what do I mean by this? So I have a grid like this. Some height and some width. So I want to do one more. So I have here n equals to, I think it's 6. Yes, 1, 2, 3, 4, 5. Yeah, it's 6. And then I have D here, which in this case is 3. And so what these n dots in a grid means I put some dots in these boxes, and at most 1 dot in each box. But they could be empty. Something like that. And then I read from this box in a matrix way. I read some basis vector. So for instance, I start in the first column and I read from bottom to top. So there is a dot in the place 5, 5, 1. If you think of it as a matrix, here's the spot 5, 1, and there's a dot. And the next dot is here. It's in the spot 1, 1. So I put a wedge and write 1, 1. Then the next one is here. So this is the spot 4, 2. And then the next one is 2, 2. And then the next one is 5, 3. And the next one is 3, 3. No, 4, 3. 4, 3. And then I have a one which is x 1, 3. So in this way, what I do, I can read off from this filling of this box with some dots, n of them. I can create a wedge product. I can create a wedge product which has, by definition, the length, the number of the dots, capital N, and the first number is between 1 and n, and the second number is between 1 and d. And you can easily check that this gives, of course, a bijection between the bases in this wedge product and these configurations. So, and if you want to understand the action of the Lie algebra, so I can take EI to be the matrix unit, which has only, it's a matrix which has only entries at the place I plus 1 of size n times n. And then you can see it acts like this. So E1 acts here, E2 acts here, E3 acts here, E4 acts here, and E5 acts here. And then if I do Fi, this is I minus 1, no, I plus 1, then the Fi acts like the opposite direction. F1, F2, F3, etc. And the green color does the same thing along the rows. And then the F upstairs. F1. And if you just look at the diagram, I hope you believe that these two actions nicely commute. So now, this gives me a basis of this space. Now let me understand, how does the GLN action looks like here? We understand how it looks on basis vectors, but how does this module look like as a module for GLN, and how does this module look like as a module for GLD? And to understand this, we can do a very easy further combinatorial game. Namely, I can read this diagram in a different way. I can make a column reading, or I can make a row reading. So I first read the first column. So in the first column, I have some entry in the fifth line, and I have an entry in the first line. That's the first column. The second column, I have something in the fourth line and in the second line. And the last column, I have something at the bottom, which is, I think, 6, and then 4, and then 1. And so these are all vectors in my first basis vector, in my V. The indices go between 1 and 6, and I can tensor them together, and I get something which is inside wedge 2 of V, tensor wedge 2 of V, tensor wedge 3 of V. So the exponents of this tensor of these wedges are the number of dots in each column. And I can do the same thing for the rows. So I take the first row. It's in the third and the first column. Then I take the second one. So this is just in the second. Then in the third one, I have nothing. Here I have 2 and 3. So I take 2 and 3. I always order them, so I have the bigger one first. And then the next one is 1. and the last one is 3. So again, I have 5, 1, 2, 3, 4, 5 different, so I have 6 different columns, 6 different rows, but one is empty, so this is not, you cannot see it. And then I do put just tensor products between these rows. And so this gives me now an element in wedge 2 of W, tensor wedge 1 of W, tensor wedge 2 of W, tensor wedge 1 of W, which is just W, and then wedge 1 of W. Okay, so why is this thing something interesting? So let me use the following abbreviation. I want to define or abbreviate this wedge A1 of V, wedge A2 of V, tensor, etc., up to something AR of V. I want to abbreviate this as wedge upper A underline of V, and the same for W. And then here's the theorem, and this is a generalization of the Schur-Weil duality. And this is called Skew How duality. So, and I should warn you, How is a name, that's a person who actually is still alive. And Skew is not a name. Skew refers to that I take wedges, so that's a skew. And the How is the person who found this result. So the statement says, the actions of GLN and GLD on wedge N V tensor W commute and centralize each other in the sense that one side is giving exactly the guys which commute with the other side. So this is what I mean by centralize each other. So this is the red version and the green version, and here's green and here's red. And now what this funny game with the row reading, column reading and row reading gives you is the following thing. When I want to understand this thing as a module for the red thing, as a GLN module, or a representation for GLN, so this is for the red version, respectively for the green version, as a GLD module. Then I can ask the question, how does it decompose? But decomposing in irreducibles is not so nice. But what is beautiful, you can decompose it not in irreducible, but in this tensor product of wedges, like this, where I sum over all A. So now from this rule, from this reading this column, what I get is the number of tensor factors is exactly the number of columns. So what I get is I have my A, which has entries A1, A2 up to AD. They might be 0. And the sum of the AIs have to be the number of dots in my picture. So it should be N. And on the other side, for GLD, I get the same picture. I have wedge upper B of W. And this B is now a tuple of the form B1 up to the number of rows. And the number of rows is N. And the sum of the BIs is again the number of dots, which is the capital N. And so the theorem is just, so you write down an isomorphism of these vector spaces by our combinatorial rule, and then you just check that it's compatible with the action. But somehow when you look at the action, when you stare long enough at this picture with the action, you, I think, believe it immediately that the theorem is true. Okay. So this is a nice duality, and the advantage of this duality in comparison to the Schur-Weil duality is that now the left-hand side, the red thing, and the commuting thing, the green one, they have the same role. So they are both GL something. And you can't distinguish, or you can't prefer, or you wouldn't prefer one against the other. Okay, so now the question is, can we somehow understand these modules here? And can we somehow understand morphisms between these guys? And this is the next goal. I will next time explain why we would like to understand the morphisms. because they are useful for categorification. But at the moment, let's just accept we want to understand the morphisms in an explicit combinatorial way. And what is behind this is the so-called, I sometimes call it universal. Maybe this is not the best word, but I don't know. The universal, or maybe not universal, web category. And I should maybe add of type A. So I want to introduce now a category which is built so that we can understand morphisms between these tensor products of wedges here. So what I want to do is I take Q being indeterminate or a complex number. And maybe it should be not 0. So and then I define the CQ. So CQ is rational functions in Q or just complex numbers. I define the CQ linear category. Web, or maybe web Q, because it depends on Q, is the following additive. So it's a monoidal category, but it's the additive closure of the strict. So remember, strict was where the associativity isomorphism and unit isomorphism is just the identities. So it's a monoidal category. It's a monoidal category where we add formally direct sums. And I have to tell you, it's generated by certain things. Is the additive closure? Yeah. Okay, so I have to tell you what generates this monoidal category. So the objects are generated by natural numbers. So that means an object is really a tensor product, finite tensor product of natural numbers. So an object is a finite sequence, say A1, A2, up to AR, which is somehow the abbreviation for the tensor product with AI in the natural numbers. Okay. And including, I should say, including the empty sequence. So that's somehow the empty tensor product. Including the empty sequence, and this empty sequence is the unit in my monoidal category. And then what are the morphisms? So the morphisms are just some trivalent graphs. So they look like this. So I again read from bottom to top. So I have a merge which goes from the object AB to the object A plus B, or I can put it upside down. I can go from the object A plus B to the object A tensor B or A B. So this is in Hom from A tensor B to A plus B. And the other one is just going opposite. Modulo sum relations. So there's only 2 relations, which I have to put. So web 1 relation, or maybe 3 relations, depending how you count. So this is the associativity, or respectively co-associativity. So what is the associativity? The associativity is saying when I first merge A and B, and then I merge the result, so this would be A plus B here, this is still C, then I get A plus B plus C. This is the same thing as if I would first merge B and C, and then I put A on the left, and then I put these two together. So I guess this is what you might think associativity might look like. And then co-associativity is just the opposite. So I would start, so I prefer to draw it from the top. So I start from A plus B plus C, then I split it into A plus B and C, and then I split the left-hand side again. And this should again be the same thing as if I would start from A plus B plus C, then split off A and B plus C, and then afterwards split B and C. So and the second relation I want to take is what I call the sin square relation, or sin square switch. So how does it look like? It looks as follows. So I have the following picture. So I start from A and B. Then I split on the left to A minus 1 and 1. Then I have here 1 and a B. So I merge it to a B plus 1. And then I split it again to a 1 and a B. So I'm ending up with a B upstairs. And then this guy comes here as an A minus 1. And I put them together and end up with an A. So this complicated guy here, okay, remove this, should be the same thing as if I switch this. So this is supposed to be a square. This is called a square. Although it doesn't look like a square, but it's called a square. So I just move it to the other side. Like that. So again, start from A, B. Then I split off the 1 from the B. So I have left the B minus 1 here. And here I get A plus 1. And then I split again off the 1. So I have left over an A here. And then the 1 comes together with the B minus 1 and gives me a B. Okay. So, but this relation would be too nice. I have to pay a little price. I have to add some rest term, which is just a few copies of the identity, like this. So this is how it looks like. So why is it called sin? So this number 1. So this is somehow the sin. So it's just a very thin strand which I somehow move between these two sides, between A and B, or which I split off all the time. And so what is this? What is this number A minus B? This number A minus B, it depends what our Q is. Where A minus B is equal to, or maybe I should just write number N. Oh, N is given already. So M is just Q to the M minus 1 plus Q to the M minus 3 plus etc. plus Q to the 1 minus M, which is exactly this quantum number, Q to the M minus Q to the minus M divided by Q minus Q inverse, in case Q is not equal to Q to the minus 1. Otherwise, this expression does not make sense, but this always makes sense. So this is either a polynomial or Laurent polynomial Q, or it's a scalar, something complex numbers. And if Q is a integer, then this is of course an integer. So and often one writes more sloppily this relation. Like this. So if you work really seriously with these web diagrams, then you give up drawing them very carefully. So you would just draw a picture like this, plus A minus B times that. And here's A, B, A, B, A, B, A, B, 1, 1, 1, 1, and the rest is then determined. So the advantage of this, it's easier to draw. The disadvantage is that you have to think what are the sort of generators which I gave you, which generate the morphisms of this tensor. Okay. Right, and maybe I should note here that this M is just the number M if Q is equal to 1. You just plug Q, if you plug in for Q equals to 1, then you get just a normal number. So in this sense, these numbers are somehow quantized versions of the normal natural numbers or integers. Okay, so let me mention a special case of this sin square switch. So if we take in this web 2, if we take in this special, sin square switch, a special case, say B equals to 0. So then then this guy disappears. This strand here disappears, and also this guy disappears completely. And if you see then what you just get the following. So on the left-hand side, you get such a thing labeled by A, and then you split off 1. So here it's A minus 1. And on the right-hand side, all this stuff disappears. And you get just, so this stuff disappears. And so, yeah, I should say, if B is 0, then B minus 1 doesn't exist. So this guy is completely 0. And then you have the identity sitting here with the coefficient A minus 0. And so I get this A in front. So, and this you should see as similar to the circle which we had last time in these other diagram algebras. A circle we always could remove and replace it by delta. In this web category, you can always remove such little squares, which are come on their own, by replacing it with this number A, depending on the labeling on the strand.
But you wouldn't really have 2 strands there. You'd really only have.
Oh, I would have 1 strand there, yeah, 6, definitely. I just copied it from upstairs, stupidly. Okay, right. So, I want to make a remark. Of course, I only gave you these thin square switches. So what about when we put here not 1, but we put here a thicker line? And I just want to say, as a remark, one can deduce somehow thick square switches from these relations. And so I think on the exercise sheet, there will be some these relations. There will be some examples. And also, so this guy actually has a very nice name. This is the bubble removal, because you remove a bubble, and I want to call it the thin bubble removal, because again, this is thin. I have a 1 here. And then so you can also, as well as thick bubble removals. And I might show you maybe later what the main idea is, how to get something like this. It's by a sort of bubble explosion procedure, which is pretty funny. But you will also, if I don't do it because of time reasons, you will see it in the exercise. And another remark I want to make, one can show the following relation. And I leave this as an exercise. So in the sloppy notation, when I start with A here and B on the other side, and I branch off a little 1 twice, and then afterwards I branch off a little 1 here. Let's see here. And I compare this with branching off a 1 from the left, branching off a 1 from the second strand, branching off a 1 here. So this is always 1, 1, 1, A, B, C. Plus, I do a guy here, and then twice here, that this is 0. So on this, when you read it in a funny way, so what do? You first do a guy which is doing something at the first and second strand. So let me call this maybe the i's and I plus first strand. So you would do first an EI twice, and then you do an EI plus 1 once. And in the second picture, you would first do something to the I strand, then something to the I plus first strand, and then again something to the I strand. And I put a -2 in front. And then in the last situation, I do something to the I plus first strand. I do something to the I strand, and I do something again to the I strand, and I get 0. And this thing is a very famous relation. So if I would write down the action of these matrix units, which I had upstairs, on an arbitrary representation, or more fancy, said in terms of universal enveloping algebras of the Lie algebra, this would be exactly the defining relations for these guys. So these are the so-called Serre relations. And if I interpret this with a Q, these are the quantum Serre relations. So these are quantum Serre relations. So they hold in the universal enveloping algebra, or quantized in universal enveloping algebra of this GLN. So that means we can see already some shadow in this web category, which should have something to do with GLN, or maybe quantized GLN. And you can do the mirror image. So you put everything upside down. So then this should be something like Fi plus 1 Fi squared minus quantum 2 Fi plus 1 Fi plus Fi squared Fi plus 1 is equal to 0.
Can I ask a quick question? If you take sort of dequantize, if you take Q to be 1, for example, what do you recover in terms of E and F? Does that make sense?
So you recover, so if I remove quantum, I have the Serre relations. What did I write? Serre relations, these are just relations in the universal enveloping algebra. So these would be then in U of GLN, if you want, the universal enveloping algebra, where this EI is just a normal matrix unit. So this EI is, in matrices, EI, I plus 1. But viewed as an element in the universal enveloping algebra. And then this is the defining relation, which comes out. Make sense?
Yes, thank you.
Okay. Right. So and these web diagrams, they were, I think, originally introduced by Kuperberg. I think with 1P. Kuperberg introduced them. And I think that's a colleague of Monica, introduced them, these webs, to understand representation theory. So he does it for pretty high generality, and in general these are extremely difficult. And then what I wrote today, this definition of type A, this is in a paper of Coates and Chemnister. Although if you look there, it's a slightly different definition. So I have much less generators relations than they have. But as I said in this remark, you can create all the other relations they write down from these small ones. So don't be confused about this. Okay. So now what I claim is that representation theory, or maybe I say it vice versa, webs. So the claim is webs control. So these things are called webs. Webs control the representation theory of GLN, and then also GLD. So that's the message. So and to make this precise, I want to consider this category, which I call fund. Fund stands for fundamental representations. So fund, or more precisely fund, now I fix, say, GLN, but it works in the same way for GLD. So this is by definition the tensor category generated, or let's say the tensor category inside representations, finite dimensional representations of GLN, generated by, oh, sorry, I shouldn't say tensor category, monoidal category. I didn't use the word tensor. Monoidal category, generated by the so-called fundamental representations. And the fundamental representations are exactly the wedge K of V. For K between 1 and N. Okay. And so actually I don't want to, I want to take all of them for all K. And I would just want to say, note, wedge K of V is just 0 if K is bigger than N. But it will be more, it's a bit stupid to include these zeros, but it will be more convenient later. Okay. And so what is this concretely? So objects of this fundamental category, so this font category, so these are just tensor products of such guys. So objects are these wedge underlined A, which are these tensor products which we had before in our Skew How Duality appearing. So it's just such things. For some finite R. For some AI in N, including the empty sequence, the empty tensor product, which we denote by K and interpret as wedge 0 of V. Okay, so now the theorem comes. So this is a theorem which says that this web category controls, in some sense, this fundamental, this fund category. So there is a C linear monoidal functor. So a functor which is compatible with the tensor product, which goes from this web category. And now I should say, I do this maybe a bit later. I have to specialize Q in a good way. So I go from this web category to this fund category. And what I just do is remember that an object, a generating object in the web category was an element A in N, a natural number. And I just map this to wedge AB. And so if I have a sequence, that means a tensor product of things like this, I just map it to wedge A underlined of E, where this A is, of course, let me just take A to be the sequence. So I take it to the tensor product of the corresponding wedges. And then I tell you, what do I do with these guys? And I wrote it already. So I should go below. Here I wrote it already this year. I don't have to copy the formulas. So this is what I wrote again. So I have web going to fund. The object A, which is a natural number, goes to the wedge A. A tuple of natural numbers goes to the tensor product of the wedges, which I denoted upstairs with wedge A underlined V. So now I have to say, what do I do to this generating guys? And I'm a bit lazy, and I just want to do it for the case where one of the entries is 1. So I have A and 1 going to A plus 1. And what I do is the following. So my notation is the following. If I have a set I of indices, so I have a basis vector like this in such a wedge product, vi1, vi2, vii, where I recall I had v1 up to vn is a basis of v. So this was my notation from before. So I just take a vector, which is just a wedge product of basis vectors with some indices here. These indices I form into a set. And because it's wedge, I want to order them so that the big indices come at the front and the small indices come later. And of course, if two indices agree, then this will be anyway 0 in the wedge product. So if I have such a thing, it's called V lower I, and I tensor with a VS. So it's an element in this wedge product down here. I want to say, what is the map which I assign to this graph, which goes from this corresponding wedge product. Maybe I should write this here. So this goes from wedge A, tensor wedge A of V, tensor V, to wedge A plus 1 of V. And this map is just the following. So I more or less wedge just these two things together. So in particular, if this VS appears somewhere in my wedge before, I get 0. And if it doesn't appear, then I just add it. So I put it in the correct order at the correct spot. But to put it in the correct spot, I have to maybe introduce a minus sign. And I tell you exactly what this minus sign is. It's minus 1 to the power, a negative power. I count the j's such that these indices ij is smaller than this s, which I have here. So that's a reasonably nice formula. And for the For the other one, when the 1 is on the left, I have exactly the same rule, apart from that my smaller becomes a bigger. That's the only difference. And then if I turn around my graph, so I want to go the opposite direction like this. So I have to take wedges and I have to split them. So I take my wedge and then I split it in all possible ways. So everything which is in this tensor product, I pick all possibilities of taking one factor, which I can put here. And then again, I have a minus sign, which counts how many indices come, which are bigger than the one I picked. And for the other version, I count the number of indices which are smaller, the things I pick. And so the claim is that this defines, so the theorem says that this defines a well-defined functor. So now you might ask the question, why is it enough, or why can I be lazy to just define it on these guys? In general, I of course have to take an A and a B here. And now I want to explain briefly this bubble explosion. So remark, it's enough to define the value on, say, thin merges or splits. And thin, for me, again, means one of the entries is just 1. So 1, A plus 1, A, either this or then the corresponding mirror image. So it's just these 4 guys which I drew upstairs. So here's the remark. Why is this true? So if I have an arbitrary guy, A, B, A plus B, then what I can do, this is what I call the bubble explosion. So the bubble explosion is the converse of bubble removing. So what I do is stupidly include a bubble here. The bubble is exploded. So it comes here. So I start from A and B, and then I have 1, B minus 1. And then I merge it, and I get A plus B. So, and from the relation we had before, we said that when I have a bubble somewhere, I can remove it, but I have to pay a price, and the price is this number B. And so I do the inverse now, so I have to take the inverse. Okay, and now if you look at this picture here, I have here a split followed by a split. Oh, maybe if I read from bottom to top, this is a merge followed by a merge. So I can use the associativity rule and rewrite this by first splitting here like this. And then I put just the other stuff on the bottom. So I get this guy, and I have A minus 1, and here 1, and B minus 1, and upstairs A plus, no, something is wrong here. This should be A plus 1. So, and what you see now is this guy became smaller. I started with a B, and it became smaller. So that means this merge at the top has a smaller B. And then here, this is a thin split, and this is a thin merge. So what I did, I reduced it to thin merges or splits, respectively smaller B. And then you can just do induction. And so that means if I defined everything on the thin ones, I have it defined already on the not thin ones. I just have to make sure that it's consistent. And this is, of course, something one has to check. And this is one of the statements of the theorem, that this is indeed consistent. Okay, so now I want to give you one explicit formula, namely what happens when I take this merge and the split. And if I take the merge and the split, then you can calculate from the formulas which I had upstairs. When I take a tensor product, what I get is always a sum of 2 things, namely the tensor product I started with plus the swapped one. maybe with a minus sign here, or -1 to the -1, which is of course the same thing. So the -1, I write if I is smaller than j, and I don't write it if I is bigger than j. Of course, it's the same thing, but I will change it in a second. And if the two things are the same, then what will come out is 0, because the merge was somehow putting wedges together. So what you see here is that this whole map, what it does on Vi tensor Vj is the identity plus -1. I wrote something wrong. The indices are wrong. Ij and here ji. So it should be the identity. So that's the first summand plus this minus sign times s. It's a swap. So that means what I wrote here, I wrote the generator of the symmetric group S2 in terms of these webs. And that's something nice, because this means I can somehow explain things which we had in the Sure Y duality, namely the symmetric group acting on this V tensor 2 in terms of webs. Okay, so now I had these -1s always in blue, and now I want to go back to my theorem. So for those people of you who know what quantum groups are, I want to sneak in a Q here. So this is my generic Q, or this complex number Q. So there's a CQ linear monoidal functor from this web Q. And so the old situation is Q equals to -1. So don't be confused about the -1 instead of the 1, in case you know the theory. I will explain it in a second. So and then I just replace all these blue things by a Q. So I remove this and make a Q out of it. I remove this and make a Q out of it. Q, and I remove this and make a Q out of it. So that means I have a functor which goes to this fund GLN, where this fund GLN is now fund of UQ GLN. So it's this quantized version. Like this. Okay. And similarly here, and now it makes a difference whether I invert or not. This is a Q, and this is a Q inverse. And then here, I get something in the Hecke algebra for 2. And this is exactly this element. So I get I don't write it explicitly. So this up to some maybe renormalization. This is exactly what people call a Kastanistic generator in this Hecke algebra. So and then the theorem is quantum skew How duality, and this is an adaptation of a result of Coates and Kemnitzer. So what does this quantum skew How duality say? So I have the left-hand side, the red one, the right-hand side, the green one. I have them in this quantum version, or if you don't like the quantum version, just forget the Q, set it to -1. It acts on this wedge product. And when I view it, this middle thing, as a GLN module, then it decomposes into this direct sum of wedges. If I view it as a module for the right-hand side, it decomposes in a similar way. But now there's something quite interesting showing up. So this is now for the specialists. So here this WQ is a Q version, so a quantum version of the natural representation of UQ for GLD. So here I drew it. I have the basis vector W1 up to WD. I have the action of the E's, which is the quantum version of the EI I+1 matrix units, which we had before, and the action of the F. And then I have the action of the diagonal matrices, quantized version of this, which just sneaks in a Q or a Q inverse. So I guess most people who know quantum groups know this representation, and this is such a so-called type 1 representation. So this is a quantized version of the natural representation. But unfortunately, when you quantize, there is not a unique way to quantize this representation. There are several ways to quantize it. So here I chose a so-called type +1 version, where all these eigenvalues of the DIs, of the diagonal matrices, are just powers of Q. So it's here Q or Q inverse, or it's just Q to the 0. I could choose another one with a minus sign. So I get minus signs here, and the representation looks like such a thing. And so the statement is to make these things really correct so that I have a quantum group, the normal quantum group on the left and the normal quantum group on the right. I have to pick, or one thing to fix this is to pick this W in this type 1 version with these eigenvalues Q or Q inverse, and the other one with these eigenvalues minus Q or minus Q inverse. And then the statement is that with this definition, the two actions commute and they centralize each other. And of course, inside there, when you take these exponents all being 1, then you get the sure while duality as a special small piece in it, as when all the AIs are 1. And then inside this quantum group, you might find the Hecke algebra in a very funny way embedded. And if you set Q equals to -1, you find inside there the symmetric group algebra, and we can recover the sure while duality from the beginning. And what I claim actually, in fact, so what I think should be clear from the setup is that when we have Skew How duality and understand it, we get the sure while duality. Okay, and when I have the sure while duality, I claim I can also go back. So I don't have time to say how this works. For people who are interested, they can look at the notes. I sketched it. I gave a sketch below, which shows how to go back. But I think I should stop here. Okay, thanks very much.
Let's thank Catharina for this great talk. And do you have questions or comments for Catharina? There was one comment in the chat by Eva that she thinks that VQ is the natural representation of UQ.
Oh yeah, so this VQ is the natural representation of this GLD, but if you look at it, it differs from this picture.
I think it's about N versus D.
Yeah, it's N versus D, that's the question.
Oh, yes, there is indeed a typo. This should be, no, this is D, the W is D. Oh, I shouldn't do this mistake.
I think it's a V, yeah, the V with the...
Yeah, the red versus green.
Mm-hmm.
Yeah, and so what is in this paper of Kautitz and Chemnitz? So they change the quantum group to Q and minus Q, which I think one should not do. And instead one should do this change. And there's two reasons for it. So one reason is categorification. This works perfectly well in categorification, and one can interpret, I will say something about this in the last lecture, one can interpret this passage from this version to this version in terms of causal duality. And the second interpretation, why one should choose this, is if you want to get something like Hovhanov homology, for those people who know what this is, one has to work with this funny thing. Otherwise, one doesn't get the correct normalization. And so I really want to include this funny -1 version, which is not the standard version. Yeah.
Thank you. Other comments or questions for Catharina?
I have a question. I don't know if it makes a lot of sense, but I'm going to ask it anyway. So I feel like there's also something that you're saying in terms of the temporally either algebra or category because of the diagrammatics you're using for this case, which like sort of match what the quantum version of SL2.
Yes.
And so one potential question is, what is happening if you does that change if you add an oriented arrow, or what is happening there? Like, does it? I don't know.
Okay, so it's very easy to make the connection. So take GL2. So my n is 2. So I would have things like this going from 1, 1 to 2, or going from 2 to 1, 1, like that. And now pass to SL2. In SL2, the second wedge is the same thing as the trivial representation. And so that means we kind of think of the two as being not existent. It's like trivial representation. So I want to view this as just a cup. And the same thing here, I just view this as a cap. And so that means these webs, these are just the GL2 version of SL2. And this SL2, I have the cups and the caps, and they are exactly the temporal leap thing. So as we saw in this overview, the Schur-Weyl duality there's a Schur-Weyl duality of temporal leap with GL2. So now put here GL2, the piece of this big thing in these terms, where you just take the A's to be 1, 1, 1, 1, 1, and then you have on the other side the temporal leap. And then do the diagrammatics in terms of these diagrams and make this stupid forgetting of 2. And then you get exactly the temporal leap diagrams. And the relations come from this web relations. If you stare long enough at these web relations, then you see that most of them just collapse, and there's only this defining relation for temporal leap left over.
Okay, thank you.
But it is better for the long run to work with GL2 instead of SL2. It has many advantages. Also, it might look a bit more complicated at the beginning, but it's better. Yeah.
Okay, if there are no more questions or comments for Catharina, let's thank her again for this very nice lecture.
Wait, I have a question.
Oh, go,
Actually,
Nicole.
Catharina, I have two questions. The first one is, so at the beginning you said, there's this somehow like, lack of symmetry between Schur-Weyl duality. So you told us about, considering the Lie algebra side. Is there some sort of duality that exists instead of considering two actions of GLN and GLD, like SN and SD, for example, or like, kind of the same question, but posed from the symmetric group side? So that's one question.
Okay, no, I don't know anything about SN and SD. I don't know whether such a thing exists. On the opposite side, so I would say, so I had also this type of duality mentioned briefly. Where you change the Y group. Also here, it's very bad to put a Y group here and a Y group here. I don't know anything. But what you could do, you can do the same thing as this Skew How. You can put here this Lie algebra or quantum symmetric pair, and then on the other side also a Lie algebra. And so maybe I should draw this because it's extremely beautiful. I put this in here. So what we saw today is that we have this wedge A of V, the direct sum over all A's, where A has D parts, and the sum is N. And on the other side, and so this was this wedge N V tensor W. And for the other side, it's the direct sum of B, wedge B W, and B is B1 up to Bn. So now let's say I want to take here this N to be actually 2m. N is 2m. And this D is 2 whatever R. So what you can do, you can go down to half of it. So when I take this V as a 2R dimensional space, I can take it as the first R plus the second R. No, sorry, this was 2m. And the W, I can decompose as the W tilde for R plus the W tilde for R. And then I can restrict to GL. So here I have GL, what did I have now? 2m. And then I can restrict to GL N sitting inside there. And what happens is that this just doubles. So I have now A primed, and the A primed is the doubled numbers. So it's a doubled lengths. And the same thing happens on the other side. And then in between, you have this GLD, no, GL, what M? GLM times GLM. This is sitting inside with a diagonal action here, acting on the restriction. And on the other side, you have GL D here and GL2D there. And you have the action of GLD times GLD. So let me summarize. So I have on the one hand side GL2M. I can restrict to GLM sitting inside GL2M. In between is GLM times GLM. When I make this big, then I should take the centralizer small. I take a GLD. Then this should be D, sorry. So I take a D here. This D sits inside GLD times GLD diagonally, and this guy sits inside GL2D. And what I have in the middle was this left-hand side was sure while dual to the type B Hecke or type B Y group. And so this would be the type B version squeezed in between two type A versions. But it's always, the only thing I know is that you make it symmetric with respect to the algebras and not with respect to the group.
Thank you. And then can I ask my second question actually?
Sure.
So all of the story is based upon like taking the alternating product of the vector spaces somehow. What if you take different things like, not just an exterior product, but like a symmetric power or mixes of these mixtures?
Yeah, so there is a version which is called Skew How Duality without skew. This is usually referring to symmetric powers. And there's this sort of analog result, quantum and not quantum. For mix, I don't know if this exists. I don't know any version of that.
Thanks. There is one other question, Catharina, in the chat by Nelima, about how important it is to work over C or characteristic 0 in the definition of the web category.
So for the web category, not at all. So this is as long as these numbers make sense here, and if you somehow were careful looking at what I wrote things like this, and I want to avoid to write things like this. So that means all this stuff makes sense over any ring, wherever this Q makes sense. So this web category makes sense. The question is, what does it control? And so the functor always exists to GLN, so it's fine. I don't know how to define quantum groups in positive characteristic in a good way. Okay, yeah, there's a definition, but I don't know somehow what we can say about the representation theory in practice, except of that it acts. Because I mean, the decomposition into idempotents or things like this of these webs is difficult. So the functor in general exists. I don't need any complex field or whatever. But when you really want to somehow write down explicit combinatorics, you want to pass to the complex numbers. Otherwise, it's too difficult. But on the other hand, one would like to, or one tries to understand positive characteristic by using these web categories and understanding the decomposition numbers. But I think it's far away from really having concrete results.
Thank you.
Thank you. Yeah, I think in 2 minutes the lunch discussions are starting. So let's thanks Catharina, and if you have more questions,